So the evidence needs to be gathered a bit more still, but we think that ring period could have lasted for 20 to 40 million years.
Hello, everyone. This is the Space Cafe podcast, and I'm Markus. Was Earth more attractive in the past than it is right now? Arguing maybe that Earth is right now way past its prime as a beautiful planet. Well, there is a scientific paper that's floating out there that argues that, so they wouldn't use those categories, beauty and whatnot, but just for the sake of making an argument, I'm taking the liberty to do so. This scientific paper argues that 500 million years ago, Earth was quite different because it had a Saturn-like ring system. How cool can it get? Just picture this. How beautiful must that have been? This theory, well, actually, it's not a theory anymore because it's a peer-reviewed paper floating out there and gaining quite a bit of attention and momentum as we speak, was written by Dr. Andrew Tomkins and his team of Monash University in Melbourne, Australia. And so according to this paper, 500 million years ago, something strange happened in Earth's atmosphere and caused a cataclysmic chain of very interesting events with even more interesting side effects. And so I was like, this is food for Space Cafe podcast land. And before we jump into discussing all this with the paper's author himself, Dr. Andrew Tomkins, I would encourage you to write into us, send us your ideas and thoughts and guest suggestions if you have some at podcast@SpaceWatch.Global. And now, my friends, without further ado, let's kick this right off. Welcome, Dr. Andrew Tomkins, to the Space Cafe podcast. Let's go. Andy, take us back into the Ordovician period 500 million years ago. What was Earth like during those times?
Yeah, so the Ordovician period, I guess it's quite a long period of time. If we started at 500 million years ago, it probably extends down to around about 440 million years ago. The start of that period, the Earth was fairly warm, quite a lot warmer than today, maybe about 6 degrees warmer than today, and it cooled down to actually, by the end of that period, down to actually the coldest time in the last 550 million years. So it cooled down to, about 5 degrees colder than today's average global temperature. Mm-hmm. And the period we're talking about, 466 million years ago, it was around about sort of 3 degrees hotter than the global average temperature. So that's a time when life was just starting to emerge from the oceans. So think animals like a mud skipper that is hopping around on the mud in the tidal environment, just starting to emerge onto land and sort of looking up at the sky around it and thinking, what's around on the land? Can I evolve and go walk around on the land? That's kind of what was going on back then.
So if I, picturing myself in the form of a mud skipper, what would the beach, the land look like? Would it look like, I don't know, a pristine, green, hilly, mountainous region, maybe, of course, depending wherever the mud skipper is at. But was it jungle already, or was plant life quite different compared to today?
Yeah, I don't know that much about the plant life because that's not really my field of geology, but it was green. The plants probably would have looked fairly different to today, but there would be no animals around there to eat the plants, that sort of thing, yet. And so there hasn't been that evolution of plants to get into really, really big trees, I would guess. You probably need to ask a paleontologist about that sort of question, but yeah. It's a time when it would have been green and animals just starting to evolve into that sort of climate coming out of the oceans is probably the best way to think of it.
The continents, before we go into the actual topic of today, but the continents, were they already formed? Were they already placed where they are today?
That's a good question. So the continental masses were formed, but continental drift was making all the continents move around over the Earth. And the people who work on reconstructing plate tectonic drift have generated movies of where the plates were back in time. And so you can Google, people at home can Google or look on YouTube, actually, plate tectonic reconstructions and see movies for the last 1 billion years of where the continents were as they drifted around across the surface of the Earth. And so the continents were there. Mountains were forming over time, over hundreds of millions of years. Continents were moving around. So all the different continents were in quite different places back then to the way they are today.
And now enter the rings. Like Saturn, from Saturn, we adore Saturn for its rings, and you're claiming that there was something similar back in the day for Earth. So how does like this now coincide with this period we just talked about?
Yep. So what we think might have happened is a large asteroid might have come close to the Earth and basically broken up as it got too close and end up forming a debris ring around the Earth. So that's how the rings around Saturn would have formed, for example. An icy moon would have broken up when it got too close to Saturn. And then the debris sort of gets distributed by gravity and sort of banging into bits and pieces over time to form a ring around the equator. And so when you look at the rings around all the outer giant planets, so Jupiter, Saturn, Uranus, Neptune all have rings, and they all probably formed by that same sort of process. There's even been scientific papers suggesting that Mars might have had rings in the past too. So Phobos and Deimos may well have formed from rings and formed back and forth from rings to moons a few times, I think. So, yep.
That's fascinating. So it's like rings are pretty much the consequence of matter coming too close into the gravity field of something else, and then the gravitational forces break matter up into bits and pieces, and those bits and pieces stay within the gravitational pull of the bigger mass.
That's right. So there's something that scientists sort of call the Roche limit, which is like a distance away from the surface of the planet, below which, closer than which, it'll break up as a body comes too close, getting pulled apart, stretched apart by tidal forces. So that's one way of forming rings. There's actually two different ways. Another way to do it is to have an asteroid or a moon or something like that run into a planet and the debris getting thrown out into an orbit that then forms a ring as well. So, for example, there's a couple of Kuiper Belt objects, small icy dwarf planets out beyond Pluto that we think have rings as well. Not us, but other people have published that. So those ones are too small to have sufficient gravity to pull apart an orbiting body. So those ones would have had to have formed rings by a collision, and then the debris from the collision forming a ring. And then Saturn's too big for that to happen, and so that one needs to have happened by a Roche limit breakup type process.
How much do we know about this asteroid? Do we know anything? Where it came from, how big it was, what it consisted of?
Yeah, that's a good question. So when we were proposing this idea, we used this kind of a weights of evidence approach where we used multiple lines of evidence to suggest that it might have formed. And one of those pieces of evidence was some sedimentary rocks that were deposited 466 million years ago that are highly enriched in meteorite debris. And so it's 100 to 1,000 times as much meteorite debris in those sedimentary rocks as is normally found in the same types of sedimentary rocks anywhere else at any other time. And so when people have analysed that meteorite debris, all of it is L-chondrite debris, which means it's a particular type of asteroid. So normally if we looked at sedimentary rocks at any other point in time, there'd be bits and pieces of other types of meteorites, very, very sparsely distributed from all different types of asteroids. This particular time, there's 100 times more, and all of it's L-chondrite material. So that's what we think the body would have been made of, a particular type of asteroid called the L-chondrite parent body, or one of the L-chondrite parent bodies that's probably broken up into multiple pieces. And so that's one of the more common meteorites we have in our global collection, something called L-chondrites, which stands for low metal stony meteorites. It's a type of stony meteorite.
Is this a local event, or would you find residue and dust from that asteroid impact all around the world? So I assume we're talking about a thin layer of asteroid residue in the ground.
Right. That's right. So it was initially found in Sweden. Some people operating a quarry found these unusual rocks encased in limestone that they were extracting. They went and asked some scientists what these rocks were. Turned out that they were these L-chondrite meteorites. And then they did further work and dissolved up limestone and extracted lots and lots of extraterrestrial chromites, which came from these L-chondrite meteorites. And then they did further work at the same age sedimentary rocks in Russia and in China, and found the same layer of meteorite debris at the same age in quite different places around the world. So, yeah, all over the world it would be. If you can find the right age sedimentary rocks, you should be able to find this material.
So this must have been a major event.
Yeah. And you can date it fairly precisely using the volcanic layers that are fairly close to the same sort of layers. And they've dated it fairly precisely to 466, or not just slightly less, 466 million years ago. So.
Wow. But it wasn't, by the way, just out of personal curiosity, this quarry in Sweden, do you know the name of that quarry? Because I just got back from Sweden like 2 days ago, and I was in Kiruna at the world's largest iron ore mine. So I'm just wondering if this was the place.
Yeah, so I just had a quick look. I think it's called, it's the quarry's in Thorsberg in Sweden.
Uh-huh.
And I think the name of the quarry is called Osterplaner 65. Just had a quick look while I was talking to you. Yeah. Yeah.
Okay. Just to get things clear for myself, we're not talking about an asteroid impact. We're talking about an asteroid, a breaking up of an asteroid in orbit. So how did the dust particles from that event come down to Earth?
Yeah, so the idea is you had the Earth here, an asteroid came very close, broke up as it went around. There's lots and lots of bits of debris in space. Over time, that if it's close enough to the Earth, the orbits will decay, it'll ray down onto the Earth, and it would accumulate in sedimentary rocks. But it's not just the debris layer in the limestones in Sweden, China and Russia. It's actually several impact craters. So there's 21 impact craters from the same period of time, and they last from exactly the same time, so 466 million years ago, for about, the ages on the craters aren't very precise, but for about sort of 20 to 40 million years afterwards. And so the idea there is you would have had this asteroid breaking up. Some bigger chunks would have been big enough to go down and form impact craters, and all the small dust would have accumulated in the sedimentary rocks. And then on top of that, the third piece of evidence is an unusual number of tsunami deposits in many places around the world as well. So you can imagine if you have impact into the ocean, the impact itself can cause a tsunami, but it also sets off landslides, underwater landslides that would also cause tsunamis. And so at the same time as all that was going on, there's three different things: the tsunamis, the impact structures, and the meteorite debris and sedimentary rocks. Yep.
Wow.
It's a very unusual period in time.
Wow. When we talk about impact, we're talking about impacts of fragments of the larger body. Those fragments that would not burn up in the atmosphere and that would make it through to the surface or explode above the surface.
Yeah, that's right. Most of them are hitting the surface. And so I think the biggest of those structures is around about 30 kilometers across, but most of them are quite small. Most of them are sort of 1 or 2 or 5 kilometers across. So out of those 21 craters, it's the biggest one. So Slate Island, the impact crater, is 30 kilometers. East Clearwater Lake is 26 kilometers across. So fairly big impact structures in the scale of things, but there are much bigger ones as well from other periods in time.
Fantastic. The Chicxulub, what was that? What was the size of Chicxulub like?
Chicxulub is huge. That's the one that killed the dinosaurs. Yeah. Chicxulub is, I think people could look it up and get a more accurate number. Last I heard it was 120 kilometers across, but it's a big one. Yeah.
Yeah, that was a big one.
Yeah.
So how much do we know about the asteroid, what it was made up of? Was it an icy asteroid or I don't know?
Yes. So before I was talking about an L-chondrite. So what's an L-chondrite? It's people can look that up if they want to online quite easily. It's something called an ordinary chondrite, meaning it's made of stony material. So it's like a silicate rock. So when you look at L-chondrite meteorites, if it was lying in the desert and it had been there for a while, they don't look very much different to other rocks. So if you sort of think of a rock, it's sort of a slightly heavier than a normal rock. And just that material sort of breaking up as it came too close to the Earth. We think there's two options. It could have been something called a rubble pile asteroid, or it could have been a solid asteroid. And so a rubble pile asteroid, as the name implies, is kind of like a whole bunch of jumbled up boulders from many impacts all stuck together by light gravity sort of thing. So that's one option. And another option is just a solid chunk of rock that could have broken up.
Okay, now so we got a bunch of particles and rocks and impact residue on the surface of the Earth, but the main bulk of the asteroid is still orbiting our planet, forming those rings, those Saturn-like rings. So how much do we know, or what's your best estimate about the dimension of those rings?
Yeah, so one way we can have a go at that question is to calculate what the Roche limit is. And so the Roche limit for a rubble pile asteroid is 15,800 kilometers above the surface of the Earth. And so if a body breaks up at that altitude, you'll form a debris ring sort of inside that orbit. So we're probably talking about a smallish asteroid, maybe slightly bigger than the one that formed the Chicxulub crater that wiped out the dinosaurs. And so the amount of debris is probably not enough to form a really, really bright ring like Saturn's rings. It also would have been a bit more dull because Saturn's rings are made of ice. These ones would have been made of rock, probably a light grey coloured rock. So it probably wouldn't have looked quite as spectacular as Saturn, but it would have been probably fairly noticeable from the ground. But it's hard to really know because it's quite hard to estimate the size of this thing too, the size of the body before it broke up.
So initially when we talked about those mud jumpers? What was the name again?
Oh, mud skippers. Yeah.
Mud skippers. Exactly.
Yeah.
So how would a mud skipper have seen that ring in the sky? What would it have looked like?
I'd love to know. I mean, you can imagine looking up and seeing this ephemeral sort of light shaded band in the sky. You can imagine looking side on at a ring in the sky and seeing like a thin plane of material. That's kind of what I have in my head, but it's hard to put a number on that because it's hard to estimate how big it was. Yeah, it'd be nice to be able to constrain it a bit better, but yeah.
I guess that a ring in the sky, matter in the sky, also obstructs sunlight. So, meaning, how much do we know if this also obstructed the sunlight in a way that the climate is affected by it?
Yeah, so that's one thing we were suggesting. If there was enough debris up there, it would shade the Earth a little bit. You could just take a look at some of the images of Saturn, for example, and you can see that the rings shade the surface of Saturn. And so if there was enough debris up there, it would block some of the sunlight onto the winter side of the Earth. So the winter side would cool down more. The reflected light off the ring might heat up the northern side a little bit more, and the summer side a bit more, and maybe increase the temperature very slightly. And so it would create a more extreme temperature variation. It might cool the Earth overall just a little bit. It just so happens that that period in time, like I was saying before, it cooled down from fairly warm conditions down to the coldest time in the last 550 million years. And so we were being fairly speculative when we were suggesting that that might have been caused by the rings. It kind of matches the time scale of the impact craters. So maybe.
Is there anything? is there anything we could learn from the fossil record? I don't know if this massive temperature delta could have affected the biosphere. And yeah,
that's a good question. So that period of the Ordovician is called the Great Ordovician Biodiversification Event. What that means is the biosphere, the life, was evolving quickly. It diversified quickly, and life diversifies quickly when it's responding to a challenge. So if the temperature is changing, if it's changing gradually enough, it'll evolve and develop and adapt as the temperature changes and the climate changes, all that sort of stuff. So whether that was driven by the shading from the ring or not is another matter. We know that was happening from the fossil record. It's plausible that it could have been driven by this large cooling event. And it's plausible that cooling event was caused by the shading by the ring. So that was we know that was happening, that diversification event. And then it's more of a question of, did our ring cause it, or was it some other process that was going on?
I just, because when we're talking about time spans that date way back in prehistoric eras, we're usually lacking an understanding or imagination, I should rather say imagination, to wrap our heads around those time spans. So how long would you say was that period? How many million years? Because I like to connect us humans as Homo sapiens on this planet for 200,000 years existence on this planet, which is ridiculously short compared to those time spans. So could you bring this a little bit into the right place?
Yeah, that's one of the tricky things about teaching geology, actually, is that massive timescale difference. It's really hard to wrap your head around. So the evidence needs to be gathered a bit more still, but we think that ring period could have lasted for 20 to 40 million years. And that's based partly on that meteorite debris and the sedimentary rocks. So the previous scientists have measured anomalous amounts of meteorite debris up to 40 million years later. And there's not really been enough sampling and analysis of that question yet. So that's something that'll be figured out in coming years. It's also based on the number of impact craters. So that period of time has an anomalous number of impact craters. So if you look at the distribution of impact craters over time, there's a spike in the impact cratering rate over time at that period. And that spike lasts for about maybe 40 million years or so too. So
could this be related to Earth passing through a cloud of meteor or a cloud of rocks?
Yeah. So before we came up with this idea, other people had recognized that there was this meteorite debris on the Earth and this spike in impact cratering rate that had been all recognized previously. And the previous idea was that there'd been a big collisional event in the asteroid belt that sent a shower of meteorite asteroid debris throughout the whole inner solar system. And that hit the Earth, and there's this big spike in debris on the Earth as a consequence of that. More recently, scientists have realized that there isn't the same spike in debris on or impact craters on Mars or the Moon, so that maybe that's a bit less possible now. So the other way that this would have happened is if there was a collision in an asteroid belt, one large fragment could have been knocked into Earth's orbit and then broken up as it came around the Earth. So very similar sort of idea, just by a slightly different mechanism. So it would have been from the asteroid belt for sure, and then some sort of collisional event to make it drift into Earth crossing orbit.
Let's go back to the conundrum of geology and time spans and the feeble human mind. When you talk about temperature differences of 5 degrees plus minus the average, these differences, this changes span over 20 million years. Is that right?
Yeah, that's right. I'd say this is So when we get onto
this is the only reaction I can have, because this is mind blowing. Absolutely.
Yeah, it's actually a really good one you're touching on here. So, how I was just saying before that the coldest period in the last 550 million years was at the end of this period. Straight after that, it heated right up to from about an average global temperature of about 9 degrees. Currently, it's about 14, maybe 15 now with the global warming.
Mm-hmm.
And it heated up to around about, 18 degrees global average, so about 3 degrees above now. And it did that really quickly. So that was a massive spike from really cold to quite warm in a short amount of time. And that coincided with a global extinction event. It's one of the 5 major extinction events is that massive heating event.
And what was the time span for this?
Maybe 5 million years or something like that. But other people would estimate that better.
Still we're talking about 5 million years.
That's why scientists are really worried about climate change, right? It's happening really quickly. Yeah.
Because this is happening in real time. Compared to 5 million years, what we're seeing right now is real time. Almost.
Yeah, exactly.
And still, it's too slow for us to be able to understand it and compute it and get an understanding for it. Maybe this is one of the reasons we're not acting, because it's too slow for our minds.
Yeah, that's what I've seen, what I think as well. It's, it doesn't feel like, 1.5 degrees in 20 years is much, or 30 years is much, but it's actually massively rapid in terms of this geological record. It's incredibly fast. Yeah.
So all in all, from your expertise, professional expertise, you would see the Earth as a very stable place over geological time spans. So the peak we're seeing right now, is a very unusual singular event, because all the other events usually take a lot longer because Earth is a stable place.
Yeah. And so there's been 5 major extinction events in the past. One of those was the big impact that wiped out the dinosaurs that caused a big change in global temperature. The one I've been talking about is the Ordovician Permian extinction event, big change in temperature. The biggest one is the Permian Triassic extinction event, which is again a big change in temperature, and all big changes in temperature. Let's leave it at that. Yep. So,
but again, over very long, comparably long time spans.
Yeah. That in geological timescales, those extinction events are short ones, but they're still longer than the one we're talking about. Or we probably don't have that really tightly constrained on how long they occurred over.
Let's go back to that asteroid. By the way, did that asteroid have a name, or do we have a name for that asteroid?
No, I haven't come up with one. Good question.
So let's call it the asteroid. Was there anything particularly interesting in it in terms of minerals or metals, or maybe even helium-3 or water or whatnot? Is there anything of interest in that you could find in the fossil record, in the geological record?
Yeah, so meteorites are enriched in elements that are not common on the Earth's surface. So in some elements, that is. So things like the platinum group elements. So the classic one is iridium, which people have recognized in the Chicxulub impact layer around the Earth. That's how they recognized that, was the enrichment in iridium. So there's a series of elements like that called the platinum group elements. So platinum, palladium, iridium, osmium, a few other bits and pieces. There's unusual amounts of nickel and chromium and a few things like that. There would have been a helium-3 enrichment, slight, but pretty subtle. Things like that. Yeah. So you can recognize it geochemically. So people have analyzed those sedimentary limestones that had the meteorite debris, and they find enrichment in some of those elements as well.
Take me back to the moment where you had that hunch that there is something you may want to look into. So where was that? When does a scientist get hit by an idea? How does that work? Where were you?
That's a good question. I like that sort of question. So I was just reading some stuff. What part of my job is to keep up to date with what other scientists are thinking and that sort of stuff. So I was reading, I came across this paper that was talking about the idea that Mars may have had a ring before from breakup of Phobos and then reformation of Phobos, Deimos, that sort of thing. And I thought, well, okay, that's pretty cool. I wonder what Earth would have looked like if it had a ring in the past. How would you recognize that in the geological record? And I sort of liked that thought and sort of rested with it for a few days. And then I remembered that there was this meteorite debris layer in Sweden, and there was this impact spike that had been recognized for the same period in time. So I looked up all that data and just checked it out, and then thought it would be a good idea to plot the positions of the impact craters on the plates and where the plates were back in that point in time. And so I got a friend of mine, a colleague of mine, to do that. She plotted up all the positions of the impact structures, and it turned out that all of them, 21 craters, were all fairly close to the equator. And the ring around Saturn is around the equator and all the rest of it. So that's really unusual. Normally when you look at the moon, all the impact craters are all over the place, and you would expect meteorites, sort of asteroids raining down on the Earth, to randomly hit the Earth anywhere. They shouldn't be all around the equator like that. Yeah. And so we did an analysis of how much of the surface area of the continents could preserve impact structures. It turns out that 2/3 of the landmass was away from the equators, 1/3 near the equator, yet all the impact structures were near the equator. So it's kind of like tossing a 3-sided coin and getting tails every time. So the statistics of that happening is really, really low. That's why we're suggesting it. So that's one of the main arguments is that one. Yeah.
How accepted is the theory today amongst your peers and fellow scientists and geologists?
I presented this at the Meteoritical Society conference just 2 weeks ago as an invited talk, and they like it. They love the idea. They love a new idea, right? And they can see the logic in it. People already know that there's this spike in impact craters. They already know that there's this meteorite debris, and so they can see that it's quite a plausible model. It's scientifically plausible, but it's also at the same time difficult to prove beyond doubt. It's hard to think of ways of proving it really well. And so part of the job of scientists is to put ideas out there, and another scientist can come along and go, oh, I could do this and that'll prove it, sort of thing. And so when I was talking to one of the other scientists after I'd given my presentation, he said, why don't you do some paleomag, I'll tell you what that is in a sec, on the impact glasses from the impact craters. So paleomag is where you take a sample and look at the orientation of the magnetic field that was formed as that glass formed. And what that can tell you is where is the latitude of that particular impact crater at the time that it formed. Yeah. So that's a better way of checking whether they're all near the equator or whether some of them might have been further away. It's like another piece of evidence sort of thing. So that might be some of the future work we could do, for example, is go to these impact structures, collect some of the right sort of rocks, and then do some paleomag to look at the ancient latitude that it was at when it hit.
Wow. How deep do you have to drill to find that residue?
It varies from crater to crater. So some of the craters are buried beneath sedimentary rocks, And so there are drill cores through some of the impact structures already. So you could go to those drill cores and use that material. Although you have to take oriented samples to be able to measure the orientation of the magnetic field properly. Other impact structures have the right sort of rocks preserved at the surface. You can just walk along and pick them up, sort of thing. Half the battle is getting there and taking the samples, but yeah.
Wow. But still, where did the rings go? Where are they?
And rings just dissipate over time. So Saturn's rings will disappear within 100, 200 million years or so. Saturn's rings are about 100 to 400 million years old already, and then they'll disappear in that sort of time frame. So rings are ephemeral, right? They don't last very long.
Where will they go? Will they rain down on Saturn, or where will they go?
Yep. So stuff that's inside the Roche limit will rain down onto Saturn. Stuff that's outside the Roche limit will drift away. That's right. That's similar to being right. So stuff inside geostationary orbit will rain down. Stuff further away will drift out. Yeah. So they eventually disappears. So another way of thinking about that too is Earth's moon actually is likely formed from a ring. And this is not me, this is other people. The way we think the moon formed is there was a Mars-sized body hit the proto-Earth, and a bunch of material was left spinning around what eventually became the Earth, and from that, the moon coalesced to form the moon we see today. So that would have been a ring of material that the moon coalesced from. What's been happening there is that the moon's gradually been drifting away from the Earth over time, and so eventually we'll lose the moon as well. Many, probably, I don't know how many hundreds of millions of years, billions of years in the future, but it's drifting away anyway.
Well, should we hurry up for that research? We need to do the moon and that moon base we want to build.
Yeah, before it gets too far away. Yeah.
Very interesting.
That's really slowly. So on our way beyond our lifetime. So you talk about geological time before, it's a long time in the future. Yeah.
Wow. Wow. Fantastic. Do you think, this is super speculative, but do you think that events like that can have something to do with habitability of a planet? Like, for example, take an exoplanet. And with the technology we're developing, we're evolving, we are seeing ever more exoplanets, slowly but gradually, directly. And now my question to you, is something like this conducive for habitability in whatever form?
That's probably a couple of fun things to think about there. So one fun thing to think about is this is potentially a way of transporting life gently to a surface. So if you had somehow had life on a moon or an icy body or something like that was sort of buried inside, and it came close to a planet and broke up, formed a ring, the rain out of debris onto the surface is a gentle way of transferring life down to a surface. And the other thing we talked about before was how a ring sort of moderates the temperature of a planet. It changes the temperature of a planet. So one thing I had wondered about in the past was whether you could terraform Venus by putting a baseball cap on it, cooling it with a ring, right? And then cooling it down and raining out the atmosphere and terraforming it that way. But that might be a bit difficult just because Venus doesn't really have a bulge around the equator. That makes it hard to have a ring and a few other bit details. But you could plausibly terraform planets that way.
I like those discussions. I like them very much. There's people who want to nuke Mars, as we know, to terraform it, and Venus is a different cup of tea. Very interesting. So, but that means the unlikelihood for life to evolve could get ever more complicated through such events. Maybe an asteroid type event triggered something, and if it hadn't been for that asteroid type event, there wouldn't be no life around. So the more I think we look into the formation of life, the more we find out how unlikely it is that life evolves. So, of course, you already mentioned it. It's not your field of expertise, because as a geologist, you do not look at the living things on the planet. But how do you see all that? Is the question, it all boils down to, are we alone? Are we alone on this planet?
Yeah. Well, so personally, I actually think the chance that there's life elsewhere in the universe is probably quite high. There's a bunch of reasons for that. So one is, when we look at the meteorite debris in our solar system, the meteorites, there's a significant fraction of them have the right sort of carbon compounds in them to have all the ingredients for life, all the amino acids, all that sort of stuff. Everything's there that's needed to make life. When you look at the element distribution in the universe, there's basically, what is there? Is it 6 main elements? Carbon, hydrogen, oxygen, phosphorus, sulfur, nitrogen, that are needed for life. And those are the most common elements in the universe, apart from helium. So you've got all the right ingredients distributed everywhere throughout the universe. There's, 300 billion stars in our galaxy, 500 billion galaxies in the universe.
It's planet, a statistical necessity.
Yes. Yeah, it's almost unavoidable. You'll have something almost exactly like the Earth. And the right elements are there. So it's probably even carbon-based life is the most likely thing, because that's what forms long-chain compounds. And water is really common in our solar system, elsewhere in the universe. So our planet is compositionally not that special.
But what makes it special, I read very recently, but this is, of course, your field of expertise, the tectonic activity on Earth is a prerequisite, some say, for the evolution of life. And tectonic activity is rare in the solar system, as far as I understand.
Yeah, that's right. I mean, I'm not sure if it's a necessity. Some people have argued that, I know. I think it's plausible that life may have started on Mars, for example. It's got the right ingredients for life. It doesn't have a magnetic field that would shield that life for surviving, and Earth has a magnetic field. That's probably more important than plate tectonics. But tectonics probably helps. But personally, I don't think it's a necessity.
Speaking of asteroids, by the way, there will be a major asteroid event in a couple of years from now. A very close call. I think only like half a year ago, science announced that it is not going to be a major impact event. So it wasn't clear for a long time that the Apophis asteroid wouldn't hit the Earth, because it's a very close call. So could this be a Roche limit type event, perhaps?
Great. Yeah, awesome. We've already asked that question and we've had to go at calculating it. So one of the astrophysicists I'm collaborating with to try and calculate some of these ideas, to model these ideas, is Dan Price, also at Monash Uni with me. And he's had a go at modeling what would happen to Apophis on its predicted orbit. And his initial models suggest that it will break up if it's a rubble pile asteroid. But I think they're pretty early stage models, and we don't know. It's not going to come within that Roche limit I talked about before. It's going to be a bit, but it's going to be, I think, within geocentric orbit.
So very close in lay terms, but not close enough for breakup. I think it's just a couple of 100 meters in diameter, which would be massive if it impacted, but still it's a small type asteroid.
Yeah, it's going to miss this. And so if it broke up, it would end up with, sort of a debris cloud moving further off and disappear off over the horizon, so to speak. But so one way to think about that too is we've NASA's visited Bennu recently, an asteroid, one of these carbonaceous asteroids. And the interesting thing about the shape of Bennu and one of the other ones was they have this sort of diamond shape. And that shape is kind of the shape you get when you have an asteroid or a rubble pile asteroid that's loosely held together, that's spinning. And if a rock falls off the surface, you lose some of the angular momentum. So that shape is something that develops. So it's at the edge of stability sort of thing. It's just about to fly apart. And when things fall off, that slows it down enough to not fall apart anymore. So when you have a body like that that's on the verge of falling apart, you just have to have a tiniest little bit of tidal stretching it, it'll fall apart. So if Apophis is like that, it could be quite interesting to see what happens to it.
There's a fun thing about the actual day Apophis will pass by the Earth. Did you know that? What day it is?
No, what's that? No.
It's a Friday the 13th. It's no joke.
Classic.
April Friday 13, 2029. That's kind of interesting
Nice.
As if written by a script author.
Cool.
Yeah.
Yeah.
Go ahead.
One of the other fun things to think about here is we were just talking about Apophis. So, and I said if Apophis breaks up, it'll just fly past and disappear. Well, one of the other interesting things to think about there is, okay, but so wouldn't that happen to this asteroid we've been talking about to form the ring around the Earth? And so one thing I wondered about is whether a captured mini-moon would be the best thing here. So mini-moons have been something we've picked up. There was one in the news just last year that it was captured by the Earth temporarily, then disappeared off again. The idea there is an asteroid comes along, gets captured by the Earth's orbit, and goes around the Earth several times and then disappears. And so in that scenario, if you have one of these mini-moons drifts in close enough and then breaks apart, that's the sort of thing that would allow all that debris to form a ring around the Earth a bit more effectively than a passing body like Apophis. So that's another thing to think about in all this.
I'm taking advantage of your expertise way beyond what we're talking about right now. The water on Earth, this is a huge mystery where it came from. Is there anything that you may know that I do not know where the water came from on Earth?
Yeah, okay. So the Earth basically accreted from debris in the solar system. So some of that debris that's still accreting to the Earth is comet particles. So meteor showers are mostly comet particles raining down onto the Earth. And there's obviously meteorites accreting to the Earth all the time too. When we look at the composition of the meteorites, the carbonaceous chondrites have lots of minerals like serpentine and smectite in them that have water in their crystal structure. And so we're talking about several % water in some of these meteorites. So some of that naturally created Earth material was made of these asteroid debris. And so the Earth would have been just built from some of that stuff naturally. So all the planets had volatile elements like, all the gases and sulfur and carbon dioxide, that sort of stuff. And then it's a question of how much was lost from impacts and that sort of thing. So I think probably impacts have quite a strong control on the inventory of those elements. So it's kind of a combination of what was accreting and then what was being blasted off at the same time sort of thing.
But still, we're talking about 2/3 of the Earth's surface being underwater, 12 kilometers deep at some places. So there must be a huge bombardment of those things. So this is, again, it's like the 20 million time span that we talked about that just does not fit my neurological equipment.
One of the fun things about that way of thinking is, yes, the ocean's really deep and all that sort of stuff, but the Earth, as the average composition of the whole Earth, is actually really, really, really dry compared to a typical meteorite. So the amount of water in the Earth is not like 1%. It's much, much less than that. Whereas a meteorite, many of them have several % water.
Mm. Mm.
So
Fantastic.
yes, the Earth has to have lost volatiles from big impacts.
Mm-hmm.
Yeah.
So your paper is published, peer-reviewed. Is there anything still you're trying, like major topics you're trying to find out about that discussion that we're having?
Yeah, there's a lot to do still. So the paper was presenting that waste of evidence, several bits of geological evidence that suggest this thing might have happened. What astrophysicists need to do now is model what's possible. Like, does it have to be a captured mini-moon? Can you numerically model the evolution of a ring and how would that evolve over time? How long could it last? So people have had a go at doing that for Saturn's rings, for example. Can you have a go at modeling the climate evolution? How opaque does the ring need to be to affect the climate? That sort of thing. We need to get a better idea of how long the ring might have persisted. And you can do that by looking at the sedimentary rocks that have the meteorite debris and seeing how long that unusual accumulation lasted for. You can date the impact structures better. You can do that paleo-mag analysis I was talking about before to see the latitude a bit more effectively. So there's lots. It's kind of like we've put this idea out there and now there's heaps of work that needs to be done to have a go at proving it wrong or proving it right.
What's the likelihood that something like this happens again in our lifetimes as a species?
Good question.
I think the biggest problem is the species, how long. So what is the lifetime into the future considering the political environment currently on Earth?
Yeah, well, Donald Trump's. Anyway, probably another way to think about it is it likely to happen in the next sort of 5 billion years before the sun consumes the Earth type of thing?
Yeah.
So one way to answer that is to look at the rings around the other planets. So I was saying before that Saturn's rings are sort of not very old and won't last much longer. The other rings around the other planets are also, ephemeral. The rings around those Kuiper belt objects are really brief. So those are ring-forming events are happening multiple times across the solar system's history. That's something I had no idea about before I started getting into this subject. And so it's kind of cool to think of the solar system sort of occasionally forming rings and they'll disappear and then they'll come back again in a few 100 million years. It's plausible that it'll happen again around the Earth. It just takes the right sort of set of conditions, the right sort of orbit for that to happen again. So it's
like a pulsating event. If you speed it up very rapidly over the eons, you would see planets having their rings and then losing them and getting them again and losing them. So there's always something going on.
Yeah, so the solar system probably looked quite different like a billion years ago. The planets would have been there, but they might have had rings or not, and Saturn wouldn't have had its rings.
Would you, if someone offered it to you, would you want to see those asteroids, the asteroid belt, with your own eyes by traveling there?
Yeah, it would be really cool. I often think about this as a geologist. It'd be amazing to have a time lapse that lasted for like 1 billion years or something crazy like that. I often think it would be interesting to live for a billion years and see it all. Imagine that. That'd be kind of crazy. That's what I'd really like to see is the whole evolving thing.
Wow.
You'd see mountains growing, continents moving, all sorts of stuff. Be amazing.
Yeah. There's a question I'm asking each of my guests at the end of the show, and that is if the call came and someone offered you a ride to the stars, a ride, in your case, to the asteroid belt or wherever, it's usually an exciting but very rapidly turning into a boring journey because the distances are vast and you can get bored pretty easily. So my question to you is, what one piece of music would you want to bring on that journey to entertain yourself? And you get to choose one tune, and that tune will be added to a Spotify playlist for the aspiring space travelers.
Oh, wow. One piece of music.
Yeah. That shouldn't drive you crazy.
One song over and over again for years.
Now you can hit stop. You can hit stop and pause. But what would entertain you?
I don't know. A song I've liked for a long time that just comes to mind is "Paint It Black" by Rolling Stones, which would be kind of a weird one to be playing over and over again for many years. So,
you should take a look. You should take a look at the playlist that is being populated by other guests, and so there's kind of very strange types of music on it, and so it's a motley bunch of human tastes. So you're fitting perfectly with your choice. And one more question. This show is called the Space Cafe Podcast, a coffee place where we can hang out and have interesting or not so interesting conversations. And now and then you go into coffee places to have a strong shot of coffee to energize yourself when you're tired. Now I challenge you to share an espresso for the mind with me or the audience, some shot of inspiration you may want to share, and whatever kind of topic you want to pick. What could be inspiring?
Okay. I was actually just thinking about a fun one the other day. You know how that they've just found that comet coming through the solar system that's from outside the solar system?
No.
What would happen if a comet like that or an asteroid like that hit the Earth moving at 90 kilometers a second, which is, 4.5 times faster than a normal asteroid? What would that look like in the geological record? What would that do to a planet? What would a much faster one do to a planet? There's some mind-blowing stuff too. It could do all sorts of stuff. How would you recognize it?
This is truly inspiring, and this will keep my mind and my brain engaged and active for a while now. Thank you. Thank you, Andy Tomkins, for taking the time and sharing your research and your wisdom and your expertise with us. Thank you so much.
No worries. It was fun to have a chat. It was nice, fun to talk about this sort of stuff.
And that is a wrap, my friends. That was another episode of the Space Cafe podcast. Thank you so much for taking the time, for sharing your wisdom and your fantastic research with us here in the show, Dr. Andrew Tomkins and your team. This is brilliant. This sheds such a beautiful light on our planet. And this is what the Space Cafe podcast is all about, at least to me. Thank you, my friends, for sticking around still on this show, still listening to this. Thank you so much. And if you feel like this is worth sharing with someone that could, this is something that could strike up an interesting conversation with someone, why don't you share the show, the link to the show with someone you like, you respect, you appreciate. And I know I'm repeating myself, but the algorithms only understand ratings and reviews. So please do so. Take those 10 to 15 seconds and rate our show on Apple Podcasts or Spotify. That would mean a lot to us and would help us grow the show to where everyone wants it to be at. Well, and that's about it for this week. I catch you in 2 weeks from now. Take care. Bye-bye.